I'm really excited to be here. This is actually my first big day out, so I'm really looking forward to chatting with as many of you as I can, but also really to hear about some of the work that's happening in the Yilgarn, especially the gold fields, and particularly from our industry speakers. Right. Before I begin, I'm going to talk a bit about some of the high-level context behind the work that we're doing, particularly in the Yilgarn and its margins, and how some of that data is feeding into driving innovation and unlocking potential in not only mineral exploration, but some other resources as well. So I hope you'll indulge me as I talk about things that might be a little bit outside of your expertise or interest, but it really highlights how lucky we are to have the Yilgarn Craton and its margins in Western Australia. Okay, so the acquisition and delivery of pre-competitive geoscientific data is what we do. It's what we've been doing for 140 years. It's why you're all here today. So that has not changed. But what has changed is that geoscience is very much at the forefront of several national and global government priorities. Let that sink in for a minute. Geoscience is incredibly important today. This is illustrated by the release, at least in Australia, of the Critical Mineral Strategy, the Net Zero Roadmap, and the Hydrogen Strategy. So we really have an opportunity as a community to not only address these challenges and opportunities, but really this is an obligation. So in order for GSWA to best respond to these changing priorities, mid-last year, we implemented an organizational restructure to better align us internally. And part of this restructure has been to establish some high-level strategic themes that each group is now working within and across. And this includes materials critical for the energy transition, carbon mitigation and geological storage, and hydrogen as a future energy source. So this list on the right shows kind of the topics that are going to be discussed today. Really great variety. Most of that feeds into the commodities critical for the energy transition. So this is really the critical and the strategic minerals. Of course, gold, although not listed as one of these, there's no doubt how important that is. So I'm not going to talk about that because the speakers are going to do a much better job of doing that than I could. I'm actually going to focus on how some of the data sets we're collecting in the Yilgarn and its margins feed into some of these other strategic priorities that we are trying to address. And I will acknowledge here that at geopolitical drivers and economics, they change rapidly, they're unpredictable. We are trying to be a bit more proactive in how we approach some of these priorities and not reactive. We want our data sets to stand the test of time. Okay, so I'm first going to talk a little bit about basin-hosted systems. So many of you might be familiar with this seminal paper that was published in 2020 by Mark Hoggard and co-authors. And they show that 85% of sediment-hosted base metals, including all giant deposits, occur within 200 kilometers of the transition between thick and thin lithosphere. So this is essentially the margins of these thick cratonic roots. And they came up with a really flashy figure, which is shown here on the right, that shows one of the magic contour intervals, so this lithosphere thickness that of 170 kilometers in this case, that really seems to capture where a lot of these deposits occur. And so this is really intended to narrow down the search space for where we look for these sorts of commodities. Now, this figure looks really compelling, but it's important to realize that particularly within Western Australia, a lack of data means that this contour interval, where this transition occurs, is very poorly known. And this, of course, is a key objective for WA Array. Our current data sets, which is mainly our kind of statewide isotopic maps, seem to suggest that this contour interval could actually be what's now shown on this map. So this is in fact really obscure. This is obscured by the Officer Basin, which is again this margin between the Pilbara and the Yilgarn. We now understand that the Officer Basin really is a good conceptual fit for the sediment-hosted copper system. And we've been collecting a lot of data to help support this. This is largely based on our legacy data and the existing stratigraphic framework that we have for this area, including information from existing stratigraphic drill holes. We've been looking at these drill holes in more detail. It's important to keep in mind that these drill holes are mainly stratigraphic and petroleum holes. They were not drilled for mineralization. But we are in fact discovering that many of these drill holes contain copper occurrences that could be of great interest. And so we're looking at this now with this lens, and we are doing further sampling and analysis of these drill holes, including geochemistry, hyperspectral data, and petrophysics that will all be synthesized into a kind of a mineral systems framework. So this is a pretty exciting result. We are also conducting ongoing geophysics to really understand the crustal and lithosphere architecture in this area. This, of course, includes WA array, which we'll get there over the next few years. But we also hope to put in some 2D active seismic lines through that area over the next few years if we're able to do that. And really, the aim is to reduce the search space for these sorts of materials in the Officer Basin in this case, but in general. Okay, I'll also just quickly point out that the Officer Basin is also an important locality where we're collecting geological data sets to fit into our CO2 storage atlas. So this is a body of work that's trying to assess the prospectivity for different basins across the state in terms of CO2 storage. It's also an important location for potential natural hydrogen. So we are looking at salt mapping and salt characteristics of diapirs in that area, which are important traps for natural hydrogen, as well as soil gas monitoring to assess the concentrations of hydrogen and helium in this area. Now, I do want to spend just a few minutes talking about hydrogen in the Yilgarn, because this just became kind of clear to me over the last little while, and I think it's absolutely fascinating, and it has very strong ties to bedrock. Okay, so the legislation for hydrogen passed through Parliament just in May last year, so this is a very emerging industry, very early days. The regulations are still to follow. So you cannot really explore for hydrogen in a standard way. This map on the right shows the Special Prospect Authority applications in yellow. So these are leases that essentially are pegged for hydrogen, if in a lack of a better word. It does not allow drilling for hydrogen, but it does allow geophysical and geochemical surveys. Now what's fascinating is how many of these are in the Yilgarn. So the Yilgarn has several of these applications, meaning somebody thinks it's quite prospective, but these are not associated with sedimentary basins. So why is that? Well, I don't think we definitively know the answer to that yet, but this diagram on the left, which admittedly is a bit hard to read, shows kind of the hydrogen factory within the crust. And what I want to highlight are these 3 bits in red, which are really where hydrogen is potentially sourced from. So the first is radioactive decay of underlying basement rocks can emit radiation that can split water, producing hydrogen. Then we have serpentinization, so the conversion of mafic and ultramafic minerals in the presence of water can form other minerals and also release hydrogen. And then the third one, which is a bit more contentious, I think, is that deep-seated hydrogen from the mantle, or maybe even the core, can move along deep-seated structures. Now the Yilgarn has all 3 of these components. So you can already start to see why the hydrogen might be prospective why the Yilgarn might be prospective for natural hydrogen. I think that's absolutely fascinating. Okay, I'm going to switch gears. You're on a bit of a roller coaster here. So the next initiative I'd like to talk a little bit about is mine waste. And this also feeds into mineral carbonation work. So we've really seen a global increase in the interest for mine waste over the last few years. This is partly to reduce environmental footprints, but it's also, importantly, to meet the growing demand for critical metals, with mine waste as a potential secondary resource. This is also, I probably should have said this at the beginning, but all these things I'm talking about are very, very new for us. So I don't need to talk about all the things that we do really, really well that we've been doing over the last 140 years. I'm talking about kind of the new things that we're thinking about. So the interest in mine waste, or the capture of mine waste data, was really kicked off by GA over the last few years, and they released the Atlas of Australian Remining Potential. I think they've recently renamed that. It used to be the Atlas of Mine Waste. And you can see in WA, they've captured about 650 sites of mine waste sites. And this shows their database. I know that's very hard to see, but that screenshot, that is, I mean, there's many more sites in there, but those are the attributes that they've captured. This includes information such as the mine location that this waste is derived from, location information, the waste type, so whether it's tailings, leach heap, the storage type, the status of that material, whether it's active or closed. In some cases, they have volume estimates, although you can see here that that's very poorly populated. And then, of course, the commodities that they think might be in there. Well, we know there's more than 650 mine waste sites in WA, so we've tried to improve this data capture. So we have now produced a database that we hope to release very soon that has almost 8,000 mine waste sites in Western Australia. These are geo-registered. These contain attributes, many of the same attributes that are listed in the GA one, but a few others. And many of these are prospective, of course, for secondary resources and or CO2 sequestration. So I think this is going to be really exciting to see how this develops. I do want to add that all this work to date has been done manually. We've had somebody there on their own initiative, I will add, this wasn't something I made them do, sit there digitizing all these features and capturing the data associated with them. Incredible effort. Our Geoscience data integration team, which I talked about this earlier, they are now working on an automated way to get this information from satellite imagery. So we hope to make this a lot more efficient, a lot faster, and it will really allow us to interrogate the MINDEX database that a lot of this information is housed in to really kind of maximize the potential of what we can do with this data. Related to this initiative, the Mine Waste Initiative, we've captured where we have our features, but for some selected sites, we actually want to characterize this material. So it's not just, capturing what potentially might be in there. We want to know what's in there. And so I will add that so far this work has largely been done in collaboration and consultation with the Sustainable Minerals Institute out of the University of Queensland. They really are the pioneers of this work, so we've been fortunate to be working with them. And for the sites that we have done so far, this has been done in collaboration with our Abandoned Mines program at GSWA. So what this kind of work entails is obviously a very good sampling strategy. We go out, we collect the samples. We then do bulk geochemistry on that material, but we also look in detail at the mineralogy. So this includes the mineral IDs, their modes, and their compositions. And we are also collecting information on the physical characteristics of this material. So things such as the grain size, the shape, the porosity, the density, water content. And this is really important when you're thinking about metallurgy and the way to extract things out of these material. So if we can start to capture some of this information, we believe that might be of very great use in the future. We're also starting to map resources that have potential for CO2 sequestration. And we've got a few collaborations in the pipeline looking at some of the research into this in a bit more detail. In situ mineral carbonation is where certain minerals, under the right conditions, can actually lock CO2 into their structure. It's essentially a type of metamorphic reaction where CO2 is taken out of the atmosphere and locked into minerals. And this is particularly relevant for mafic and ultramafic rock types or lithologies. So we can map, obviously we've got a map of these sorts of lithologies across the state, which is what's shown on the right, but also the mine waste can potentially add a lot of impact into this theme. And so just this pie chart here on the bottom left, these are some back of the envelope calculations as to the potential for this kind of work. So the theoretical maximum of CO2 sequestration from these rock types is on the order of 140 gigatons of CO2 compared to our emissions at about 80 megatons. So the point is that even just a small percent of efficiency could potentially offset our carbon emissions, which is pretty exciting if that works. Okay, so thank you for that whirlwind. 2024 was an incredibly busy and exciting year for us. It's been a great time for me to step into this role and reap the rewards of all the hard work of our fantastic geologists. This just kind of summarizes some of the work that we've done, the things that I'm particularly proud of. This is my favorite list of what we've done. A lot of these things we will be talking about today. Some of these things I've already touched on, and if any of these interest you and you want to hear about more of them in detail, I myself would certainly be happy to chat with you, as I'm sure many of our geologists that are here today. So I hope you have a great day, and thank you very much for your time.